Thank you very much for the invitation to come here. Very happy to be here. And as Till said, my background really is in both academia and survey work and in industry. And I think one of the points I would like to make today is that I think, based on Arctic geology, that collaboration between industry and survey and academia can help a lot to increase the efficiency of exploration, both in the Arctic region and elsewhere on this planet. So the Arctic is known to host exploitable mineralizations. There's a series of mines, Polaris, Nanisivik, Black Angel mines, all lead zinc mines that are presently closed. There's a Norilsk deposit up here, Norilsk Ternang, that's probably never going to run out of ore. And then there's a couple of other deposits that are known, including the Citronen Fjord deposit in North Greenland that is currently being developed. They got an exploitation permit, but has not been opened yet. I think it's common with all these deposits is that they occur in sedimentary basins, and I think that particularly the Arctic regions are has a characteristic of having well-exposed sedimentary basins, which is a point I'll get back to in a second. So most I'll be talking about today is concerning North Greenland, which is a place that I know of, but I think a lot of the aspects of what I'm talking about today will apply equally well to the high Arctic in Canada and Spitsbergen and the Siberia. So the talk is in really 4 points here. First, the logistical challenges that are to exploration and mining that in turn form barriers, of course, to the exploration industry. I will touch on geology of North Greenland and mapping and exploration history. And then finally, the main point really, how Arctic geology, the insight gained from studying Arctic geology can help exploration industry to be more efficient. So this is one perception of what the high Arctic looked like. And I think this is a painting by Friedrich Baggin from about 150 years ago. In fact, this is probably not far off from a lot of the time when you look at the Polar Sea, except maybe for the wooden shipwreck somewhere here. But it's also true that for substantial periods of time in the summer, you have very well exposed ground, no vegetation, basically an Arctic desert with very little precipitation during the summertime. So although the fjords may be frozen and therefore a hindrance to access by ship, certainly this is a geological wonderland for geologists and explorationists. So the logistical challenges, of course, I have to touch on here are threefold. There's basically the climatic that imposes the also remoteness and therefore the access that will be heavily reliant on technology. And then the barriers that they form to the exploration industry in terms of costs, time, and to some degree also scarcity of information and data. So first, the climate challenges. Really, there's a window in North Greenland for about 3 months where snow is off the ground, starting in end of May, early June, for the lower elevations, and then into the summertime. Peak is about early August, where most of the ground is snow-free, and then ending in early September with the first snow on the ground. As you can see here, some of the fjords may break up. Some places that can be exploited particularly in the western part of North Greenland, where you can actually access by ship coming up from the west coast of Greenland. That is not possible, at least with common technology. So, of course, icebreakers do exist that can enter this fjord system here, but usually it's blocked by the polar ice. Right, so there's a time window where you can work on the ground in North Greenland of about 2 to 3 months. Then the remoteness is, of course, because there's no permanent population. There are 2 military bases alert on Ellesmere Island in the Canadian side, and then Station Nord in the eastern North Greenland. It's a Danish military outpost. Both of them had long runways that can accommodate C-130 or Antonov planes. And at least Station Nord is relatively open also to civil traffic, but there's no scheduled flights or anything, so you really have to go out and hire your own C-130 to haul your ship's things in. And then all of North Greenland is peppered with short runways for twin otters that service the Danish patrol that looks after North Greenland in the spring time. So once you establish yourself alongside one of these runways, you have actually reasonably good access by air transportation. So, and I just say the reason I put Granach here, Granach is the northernmost town, populated place in West Greenland, so it's about 200 kilometers south of this place here called Washington Land, which I'll get back to in a moment. And this is also the southern coast of Washington Land is the closest you can get with a ship most summers. But because, as you could see on the preceding slides here, the fjords don't really break up until rather late in the season. So if you want to carry out field work in North Greenland, depending on provisions and fuel, etc., coming in by ship, then you have to plan the year before and bring it in late in the summer for use in the subsequent years. So obviously, getting around North Greenland is heavily reliant on air transportation, either by skis when there's snow on the ground, or tundra wheels with the twin otters, and obviously the helicopter to bring geologists around in the field. And these uses about 1 drum of fuel per hour. So there's a need for constant supply of fuel. This is a ship that was brought up by Avanar Resources in 2012 to haul in about 400 drums of fuel to southern Washington Land. And just to give you so all of this is very costly, and to give you an impression of the cost that is involved in operating in North Greenland, we can look at the price of helicopter fuel. So about 200 liters an hour goes into a helicopter, and when you purchase the fuel in drums somewhere in Europe, it's about $1.20 a liter, which is about 8 Danish kroner. So once it's shipped to Nuuk, the capital of Greenland, which is about, you can see the map of Greenland behind here. So Nuuk is situated down here somewhere. It has now increased about 50%, and it's now at a price of 12 kroner per liter. Then it's hauled up to Washington Land here by ship, which costs another 9 kroner. Then you have to get it on shore, another 4 kroner per liter. Then you transport it across Washington Land to Petermann Camp, where the base camp was established, adds another 19 kroner. So by the time that you want to fly out in the field with your geologist, you are up at about $7 per liter, which brings the hourly price for the helicopter up to nearly $4,500, which is about double of what it normally would cost elsewhere in Greenland, which is already pretty high. So obviously, this is not really a country for junior companies. So just about the cost, but there are more barriers, namely also, okay, well, just to summarize here, the cost of 2 month, it turned out to be 2 months altogether by the end of the day, operations here in Washington land. 8 geologists and all of these samples and helicopter hours, etc., was about $2 million, which is about double of what a relatively decent drilling project somewhere in Sweden or Finland would cost. So the cost is one of the barriers. Another barrier is the time it takes from planning your exploration project and making all the signatures and hiring ships and bring provisions up in the field so it's ready for the following year. It takes about 1.5 years, 18 months of preparation. So as a summary for the time here, there are several aspects of the time that forms a barrier to exploration. Namely, for instance, so there's this. Let me see the pointer here. First of all, you only have the exposed ground for a relatively short time window, which can be expanded if you do ground geophysics or airborne geophysics. It can also be expanded if you first establish your logistics platform somewhere and want to carry out drilling. Then you can probably operate more or less year-round. For the early stages of exploration, that's not possible. So the result of all of this is there's a very significant reduction in the efficient time that you can collect geological data. And also because of a lot of the junior exploration industry is reliant on retail investors, therefore you have to keep them happy with the constant release of news. That's not possible when all you can really say is that we are planning yet another, signing a new contract with this and that, etc. There's no data coming out of this for long periods of time. So the last one, well, I just want to make one point here, namely, I think that, considering that still in the order of 70 to 80% of all new discoveries are made by junior exploration companies, I think that that is really one of the major barriers to exploration in the Arctic. Junior exploration companies can't really make it into North Greenland or Ellesmere Island or some of the other places in the high Arctic. It's too costly for them, and I think there's a couple of exceptions to that, but that is not to say that it's not an area that can yield new deposits, but it just takes a lot longer engagement to work it up. The last point here is that there's a scarcity of geological data, but I think that is probably more perception than it's reality. It is true that compared to the rest of Greenland, so all of Greenland is well covered with geological map at a scale of 1 to 500,000, but for 100,000 scale map sheets, of which there is about, 63 covering mostly West Greenland and East Greenland. Only 4 of these are published for North Greenland. So, okay, so there is certainly an uneven distribution of knowledge of geology. But on the other hand, to a certain level, you could say that this is counterweight in terms of the amount of exposure that you find in North Greenland. As one example, but which is actually true for most of Greenland, you could claim. So I'll speak briefly about the geological mapping campaigns that really started out about 100 years ago, where most of the geology was mapped by dog sledge, or from dog sledge, and one of the pioneers in this work was Lauke Koch, a famous Danish geologist who insisted on using the latest technology. And at that time, it was, amongst these, it was introduction of planes in mapping geology. So he used these planes very extensively in the 30s, actually the first flights he did was already back in the 1920s, to make a comprehensive coverage of photos of geology that could later serve as a background for geological mapping. So the first one of these, this is one of the first geological maps, mainly drawn by from dot sledging expeditions from 1922, and it was later released by the Geological Survey of Greenland, later becoming Geological Survey of Denmark and Greenland, in expeditions in the mid-60s, and most prominently in two bursts in 1978-79 and then 1984-85. Much more heavyweight expeditions. This is one of the typical GGU campsites in North Greenland, 2 helicopters, several twin otters servicing, and resulting in a comprehensive geological model for North Greenland that I'll get back to in a few seconds. There's really been 3 to 4 major campaigns also with respect to mineral exploration activities, starting out with Green Arctic Consortium in the 1960s, which was really a very sort of reconnaissance work, followed up by JV between Platinova Resources and Nanisivik Mines, and later on in the 90s, late 90s, between Platinova and RTZ, that led to the discovery of the Citronen Fjord deposit in 1993. Later on, worked up by Ironbark Zinc, who is presently holding the deposit and does a little bit of exploration around the deposit. And then by Avanar Resources, partly in JV with Boliden in 2010 to 14. The data background is not as bad as you would think. During the GGU years, late 70s and mid 80s, there were, along with the geological mapping programs, there was also a very significant regional stream sediment sampling program that covered, actually ended up covering most of Greenland, but North Greenland is reasonably well represented here. And this is partly the background for the work that led to the discovery of the Citronen Fjord deposit. The first year in 1992, work was concentrated here in the western part, with the Citronen Fjord escarpment here showing up very well in terms of Zinc anomalies, which is really the transition between the carbonate platform being exposed here in the south towards the deep water facies towards the north. And so in 1993, this was explored to the east and leading to the discovery of the Citronen Fjord deposit. And you're not in any doubt when you land arrive in the valley system here, which is like a moon landscape of gosens. But I think that this discovery is probably one of the last that can be made from the surface expression of the deposit itself. So I'm now turning to the next point of this talk, namely that there's a lag in efficiency for the mineral exploration industry at the moment. They're not performing very well and have not really been when you look historically, and particularly not if you compare to how the oil exploration industry has developed over the years. So here's a quite well-known plot from Shoddy presenting this some years ago, and it shows the depth of discovery since about 100 years ago, with the average depth of discovery for oil deposits or oil reservoirs, oil fields, which is 2 times this y-axis here. So it's about between 4,500 and 5,000 meters today, whereas the average depth of discovery for mineral deposits is for gold still at 150 meters. And a lot of the deeper deposits here that have been found, this is green for copper, nickel, and zinc here, they are really discoveries that are made adjacent to operating mines, that is brownfield exploration. So there's a significant inefficiency in the mineral exploration industry here. And I think that the reason for that is that the hydrocarbon industry has, over the past 40 years, developed the petroleum systems concept. And I think that this is where, I mean, there's a similar recognition that mineral systems approach should be the backbone, really, of any good exploration strategy. But it is limited. It's not exploited to its full degree if it is in use at all by a lot of the junior exploration companies. And the reason for that is that we have this lack of robust 3D geomodels for the underground. And this is where the Arctic geology comes in, as you can see here, in the background, exceptionally well exposed ground. So my point here is that the Arctic provides a insight into the architecture of sedimentary basins, particularly sedimentary basins, so that we can study a lot of the processes that ultimately will be controlling mineral deposits in sedimentary basins that account for about 100% of the world's production of zinc, for instance, and a high proportion of copper and lead, of course. So Greenland has more than 10 major sedimentary basins spanning about 2 billion years of Earth's history, ranging both from almost virtually undeformed to heavily tectonized. Some of them are known to host mineral deposits, some not, but I think the point here is that you can study these at a level of detail that has not been done before. This is a qualitative 3D model that was coming out of the studies by the GGU, the Geological Survey in North Greenland in 1991. This is about 800 kilometers span of geology from east to west, North Greenland, with the platform carbonates and deep water sediments here. But it's still at a very early stage, but this is the level of exposure that you see. It's truncated by numerous deep fjords and glaciers that exposes mountain walls. So that my point here is you can go here, you can look at details of alteration, study these fluid migration pathways, etc. At a level ranging from the resolution of the electron microprobe or a scanning electron microscope to hundreds of kilometers scale using stereo images and remote sensing spectral imagery. So spanning about 11 orders of magnitude. So geological mapping can be done at a completely new scale here. We heard about today, and they talk about mapping these manganese crusts in the abyssal plains, and a similar approach has been developed for taking georeference stereo photographs of mountain walls here, and also hyperspectral imagery that can be used for addressing very details of geology in 3D, leading to development of 3D models with the fourth dimension, namely the time, that goes into, that can portray alteration systems, fluid interaction, fluid rock interaction, etc. And the software that can handle and visualize these kind of data is already, to some degree at least, being developed. Here's an example from the result of the ProMine project, which was a FP7 project that resulted in publishing a book about developing 3 and 4D models of mining camps in Europe. This is one model here for the Skellefteå field in northern Sweden. And I would say here there's an opportunity for the minerals industry to work together with academia and geological surveys to put all this information that you can gather from studying these extremely well-exposed sedimentary basins and put it into software that can visualize and constrain the geological processes that act in sedimentary basins, both from deposition through stagnation and destruction. And thereby be applied to places like this, which is the Sechstein Basin, German-Polish Sechstein Basin, that contains one of the biggest copper silver deposits in the world, but where all we know here really comes from drill intersections and a few road cuts. Thank you.